We place two beakers over identical gas flames. The beaker on the left holds clear water. The beaker on the right holds cooking oil. We have set this up with strict controls. The mass of the liquid in each beaker is exactly the same. The heat output from the Bunsen burners is identical, and both liquids start at the exact same room temperature. Yet, as the seconds tick by, the two liquids react very differently. The temperature of the oil skyrockets, rapidly approaching its boiling point. Meanwhile, the water barely warms up at all. This is a striking discrepancy. The exact same amount of thermal energy is entering both beakers, but their internal temperatures follow completely different trajectories. These results only make sense if we separate two concepts we often treat as the same thing: heat, the actual transfer of energy, and temperature, the measure of that energy. They are joined by a material property called specific heat capacity. To understand why the oil boils while the water remains cool, we need to mathematically isolate the variables that determine how much heat an object actually requires to warm up. We start with heat capacity, represented by a capital S. This equals the amount of heat supplied to a substance, delta Q, divided by the resulting change in its temperature, delta T. But there is a glaring limitation here. This equation only measures a specific intact object as a whole, like a whole frying pan or a whole brick. It does not help us compare the underlying materials themselves, like our water and our oil. To create a universal standard that works for any substance, we have to expand the math to account for the exact mass of the material we are trying to heat. By introducing mass, lowercase m, into the denominator, we create equation 10.11, giving us lowercase s, specific heat capacity. This establishes our standard unit, joules per kilogram per Kelvin. A joule represents transferred energy, and Kelvin is the scale for absolute temperature. This works perfectly for solids and liquids, but physicists run into a wall when applying this to expanding gases, where measuring precise mass in kilograms is highly impractical. To fix this, we swap mass for moles, represented by the Greek letter nu, to introduce equation 10.12. A mole is simply a unit used to measure the exact amount of a chemical substance. This creates the molar specific heat capacity, represented by a capital C. Calculating this for gases requires strict environmental controls, because as gases heat up, they physically expand and push against their containers. Because of this expansion, gases actually have two distinct molar-specific heats. One applies if you lock the gas in a rigid box, so the volume is constant, known as CV. The other applies if you let the gas expand to keep the room's pressure constant, known as CP. By adjusting our variables for mass or moles, we now have the mathematical formulas required to calculate the exact thermal resistance of any solid, liquid, or gas we encounter. This is a bar chart comparing the specific heat capacities of common materials. Heavy metals offer very little thermal resistance. Lead sits at 127 joules per kilogram per Kelvin. Copper is at 386. Aluminum hits 900. Then there is water. Its bar towers over the metals, clocking in at 4,186 joules per kilogram per Kelvin. The math shows us that water requires vastly more energy input to raise its internal temperature by a single degree than almost any other common substance on Earth. This resolves the mystery of our beakers. The oil heated up quickly because its specific heat capacity is low. The water absorbed the exact same amount of energy from the burner, but because of its massive specific heat, it acted as a thermal shock absorber, easily swallowing the heat without its own temperature rising. We engineer around this thermal shock absorber effect every day, specifically when we need to manage extreme mechanical heat. This is exactly why water is pumped through the radiators of internal combustion engines. It can absorb immense amounts of waste heat from the moving metal pistons without boiling over and destroying the engine block. This exact same thermodynamic math scales all the way up to our planetary weather patterns, dictating the climate on our coastlines. During a hot summer day, land heats up quickly, but the high specific heat of the ocean keeps the water cool, driving a cool sea breeze inland. At night, the land loses its heat rapidly, but the ocean holds on to its stored thermal energy, staying warm and reversing the wind direction entirely. We can see the inverse of this by looking at biomes that lack water's thermal shielding capabilities. In a dry desert environment, the sand and rock have low specific heat capacities. Without water to absorb the sun's energy, the ground temperature skyrockets during the day and then drops the moment the sun goes down. Specific heat capacity is a practical physical limit. It dictates how we design the engines that power our industries, and it regulates the thermal cycle